In this question, we've got a Venturi meter, which is inclined in this case. So it's not horizontal, unlike most of the ones we've been looking at. And there are two piezometer tubes, one connected to the upstream section and one connected to the throat section. And we don't know the velocity, the inlet velocity or the throat velocity. However, we are told in the question that the velocity in the throat is twice as large as the approach. So therefore we're asked to find what is the velocity in the throat. So for this we need Bernoulli's again. Okay, so we write it out between 1 and 2. So the static pressure plus the dynamic pressure plus potential pressure is the same at each point. So we just need to find the values for or find functions for the pressure or the velocity at each of these points. So looking back to the question, we can work out what we know. Well, we don't know what the static pressure is at 1 or at 2 for this matter, but we do know, because they're connected to these piezometer tubes, we can work out the pressure. So the pressure at 1 is equal to rho GH in this tube, okay, rho GH, plus atmospheric pressure, because that would be pushing from the top. So we end up with P atmos plus rho G times 1, because it's 1 meter. Now at 2, we got the same thing, it's P atmos plus rho GH2. Now H here is 0.1. Don't get confused about this. The fact that, this is 0.4 meters off the ground. So it's not 0.5 in here because the level isn't 0.5 above here, it's only 0.1. It just happens to be 0.4 meters off the ground, okay? But the actual height in the manometer is 0.1 meters, not 0.5 meters. In terms of Z, because we assume in that that 0.1 is on our datum, we can set Z1 to 0 and Z2 obviously then be 0.4 meters. And then the final thing that we know from the question is that we don't know what either of the velocities are, but we were told that the velocity in the throat is equal to twice the velocity upstream. So C2 is equal to twice C1. So we can plug all these things that we've found out, all these assumptions, into this equation. So you can see P1 is being replaced by P atmos plus rho G1. This term stays as it is, Z1 is 0. We've also got P2 is equal to P atmos plus rho G 0.1. This dynamic term has been modified because C2 is equal to twice C1. But just notice here, the whole thing is squared, okay? So it's C2 is equal to twice C1, so it's 2C1 all squared, okay? And then obviously this term's unchanged. So that's what we had on the previous slide. So before we go any further, we can do some cancelling here. So you can see that this term will disappear because it's times by 0. We have P atmos on each side, so we can minus that from each side and those terms disappear. And here now we can see that each one of these terms has got density in. Now we weren't actually given the density of the fluid in the question, and you can now see that we don't actually need to know it, because if we divide every term through by density, all those terms disappear. So we now end up with G half C1 squared, 0.1 G plus a half 2C1 all squared, and obviously this GZ2 term. So that's what we've got here, moving everything that we've cancelled out. So now, if we rearrange, start collecting the terms, so we've got G minus 0.1 G gives us 0.9 G minus Z2G over to this side, that we get this term, collecting all the G terms together. And if we collect our C1 terms, we've got 4 over 2 minus 1 over 2 gives us 3 over 2 C1 squared. So we can now rearrange this in terms of C1 and put in the values that we know. So we know that Z2 is 0.4, and we end up with a value of 1.81 meters per second. Okay, now that's not quite the final solution, because we were asked to find the velocity at the throat, not the velocity of the inlet. But we know that the velocity at the throat is twice the velocity of the inlet. Therefore, if we double that, we end up with an answer of 3.62 meters per second.